And let's go back a second and look at the functional groups that we talked about on Wednesday, and make sure we realize that this is not trivial. This is not easy. This is tedious. This to me is like anatomy, right? You're looking at some system and it's like, okay, all these little bones and what have you, and you have to memorize them all. You have to memorize what they look like. It's boring, no doubt. It's tedious. But it needs to be done so that we can converse in a sort of a high-level way. So when I say ketone, you have an idea in your head what a ketone is. I say alcohol, you know what an alcohol is. And we learn them now, and we just hammer at them for 2 semesters. So I mentioned that the semesters are broken down into some logical sort of ideas, where the first semester is all about the sort of pieces that you need to play with and the rules that you have to obey. And we lead into mechanism when we talk about reactions for the second half of the first semester. We stop with the alkynes, and then we move into the second semester with the benzene rings, and we talk about ketones. Ketones are hugely important in biology and in engineering as a functional group to be able to knit things together. So you need to recognize a ketone. What differentiates a ketone from an aldehyde is the number of carbon groups attached. A ketone has 2 carbon groups directly on the carbonyl. And the vast majority of the chemistry in the second semester is carbonyl chemistry. It's a huge, huge subject. So what I've got here is a ketone. You can see, I think, fairly straightforwardly. These 2 R groups, we haven't really mentioned what an R group is just yet, but we should mention that R is generic. R is any carbon-based piece. But why do we choose R? Well, R is not on the periodic table. There's no element R. So the organic chemist chose R as their generic functional piece that can attach to a functional group and exemplify bigger, more complicated molecules. So in this case, for a ketone, they both have to be R groups. You can start out very simply with something like acetone, in which they're both CH3 groups, and we'll name these things as methyl groups in the near future. And you can work up to very complex, very important biological systems like hormones, in which this ketone is embedded in a much bigger structure, much more complicated. And you'll find very quickly that this can be frustrating because there's no carbon written here, but you have to remember that's a carbon, and that's a carbon, therefore, by analogy, that is a ketone. So practice, use your flashcards, make those things, have them with you, practice, and this shouldn't be so bad. Michaela? Yeah, go on. Yeah, that's just a R prime, that's just saying it's something different. But they can be symmetrical, they can be unsymmetrical, we'll see a lot of that later. But that's a ketone, not an aldehyde. And you're going to see functional groups now, for the first half of today's class, that look a lot alike. And if you're not on top of this stuff, things go wrong pretty quickly. So I'm looking now at what we're going to call aldehydes. Aldehydes are different. They do different chemistry. They will do different oxidation chemistry. They're not as stable as ketones. We'll see rates of reaction differ between these molecules. And this now has swapped out one of those carbon groups for a hydrogen. So any aldehyde must have at least 1 hydrogen attached. And that will be very, very important for some of the very heavy mechanisms next semester. Aldehydes are quite different. They do different biochemistry. They do different organic chemistry. And the definition down here is we got rid of one of our carbon-based groups, and we put in an extra hydrogen. That's all it is. It has to have at least 1 hydrogen. And we talked about examples where we could put some more complex stuff in. This one has an aromatic arene type system attached, and it's an aldehyde. This one is an aromatic and an alkene, and it has an aldehyde. So we're building up to polyfunctional molecules. And in recitation, what I did on Wednesday and what I will do on Monday is throw some big molecules at you so that you're not scared about these things, you're not intimidated by these things. Well, moving on, we can think about other places we need to go here in terms of functional groups. The carboxylic acids. Now, there's a clue in the name here. These things are acidic. And when I get into chapter 3 on Monday, which I think is the beginning of the difficult stuff, you must recognize the functional groups and recognize that they're named off and give you a clue. The carboxylic acid here is an acidic. And you've dealt with these things in the past. You took the general chemistry sequence here. I think you do a pKa analysis in the freshman lab, so you've seen some of these things before. And you'll first off say, well, isn't that an alcohol? And the answer is no, because it has something extra. If it doesn't have that double bond in there, it's an alcohol. But if it has that carbonyl attached to the same carbon as the alcohol, it's now more important. It's a functional group called the carboxylic acid. So the carboxylic acid is this, all of this piece here. Again, we can see the R group can be anything you want pretty much. We'll build up complexity as we go, but those carboxylic acids now will show up in nature a great deal. You can see nicotinic acid, okay, over here, carboxylic acid portion. Again, the carbon's not drawn. After Wednesday's class, we should be able to see that that's still there, even though we've not put it in. And we'll find now that as we go into biochemical type compounds, these become very important. Citric acid is important. You can use this for stripping paint and stuff like that. It's quite useful. It has 3 carboxylic acids. What else is in there? What's the other functional group in that molecule that's not a carboxylic acid? Alcohol, right? So this is an alcohol, polyfunctional. The word poly will be important to most of you in the future. Glutamic acid is one of the 20 amino acids that you have to memorize when you take biochemistry. It's one of the basic building blocks of proteins, a lot of which will do catalysis later on. And you'll see now that we have this carboxylic acid and this carboxylic acid. Are we okay back there? Calm down. All right. We haven't dealt with this functional group yet. We will in a few minutes, but you can definitely see the carboxylic acids. They're not alcohols, and you can tell when people study properly, they can see the difference. Are we okay? All right, let's get going. Acid chlorides. You will not see a lot of this semester, but you will see a huge amount next term. These are derivatives of carboxylic acids. Nature doesn't give us many molecules with chlorine in there. And that's a pity, because chlorine is very powerful and very useful to organic chemists, because we can replace it. We can use it as a substitutive type group. We can replace it with other pieces, and we can start to do this molecular sort of construction by replacing chlorine. But there are two names here, and again, this is historical: acid or acyl. Acyl is this group. It's a carbonyl group with some electronegative piece attached. And I'll swap out that electronegative piece now and give you the different functional groups, but the acyl or acid is the same thing. And it's derived from an acid. You will actually make the carboxylic acid turn into the acid chloride next semester, and then that becomes very powerful as a reagent. So examples of this: oxalyl chloride, you might have heard of some of these things: oxalyl chloride, benzoyl chloride, acetyl chloride. You don't know the names yet. We haven't done the nomenclature. We will spend quite a bit of time on that to give you a systematic way of doing this, but we haven't done that yet. Oxalyl chloride, there's the basic framework. There's the acyl group with the chlorine attached. Down here, the simplest one probably is this, which is acetyl chloride. There's the acyl group, again with the halide attached. So different. The chloride is a clue, right? We've only done alkyl chlorides and acyl chlorides, but they sound the same, and to many people they look the same. So practice this stuff, do a study sheet, which is just condensing your notes at the end of the day, do some flashcards, and make sure you practice. Moving on, this one always confuses people. People do not like this functional group. It's a pity, because it's very important, right? It's what holds your DNA together. It can be very important as a reagent next term in terms of using this thing. This is an acid anhydride. Now, what does the word anhydride suggest to you? What's it derived from? Anhydrous, which means what? What does anhydrous mean? It means you've taken water out of something, yeah? You've dehydrated it to make it anhydrous. So the word anhydride comes exactly from that. The industrial process that the engineers are responsible for to produce this stuff is to take a carboxylic acid and then heat it really high with some catalyst and remove water. And if you do that, two of these molecules come together and they give you a molecule that's missing a molecule of water, an anhydride, and this will be very, very important. So I've got two carbonyls. It is not simply a carboxylic acid. There's no hydrogen on the oxygen, and it sort of mirrors itself over here. For now, we'll worry about, it's the same sort of thing on both sides. You have two carbonyls attached through a central oxygen. So this is an acid anhydride. Again, the acid suggests that it comes from the carboxylic acid. You will see all types of examples of this in the near future. We can see acetic anhydride. Why is it called acetic? Well, it came from acetic acid. The names here will be quite logical when we get there. But we again have to worry about the fact that we have two carbons there. And if we're not paying attention, you'll think that's an ether, because it's the same sort of building block, right? You have a carbon, oxygen, carbon, but there's more to it. It's a more complex functional group with the two carbonyls there, which we have to call something different. And its chemistry is quite different to the ethers. It certainly is not an ether. So the anhydride there gives you the clue that the oxygen is coupling those two things together. Benzoic anhydride, you'll find this is very useful later on as a precursor for radicals and things like that. We'll see the idea now. The benz part here comes from benzene, and then the oic part is because it came from benzoic acid. That's the second semester, but we need to see what these things look like. This thing is kind of buried in this cycle. This is maleic anhydride. We have an anhydride. What else do we have? What's the second functional group in that system? An alkene. Okay? The anhydride thing, again, make sure we see it. Esters. You will spend a lot of time worrying about these things if you are an engineer. Polyesters, one of the basic main commodity chemicals that are produced on mass scale in this country. These are called esters. And this differs from a carboxylic acid but in a very simple way. We got rid of the hydrogen. If we got rid of the hydrogen, we don't have an acidic proton there anymore. So the esters don't tend to be acidic in the same way the carboxylic acids are. I can see here the carbonyl again. I can see my acyl group, so it belongs to the same family. When we talk about the second semester chemistry in the new year, we'll say that it breaks down into two different types of chemistry, one in which we add things and one in which we replace things. This type of compound replaces. This is a good functional group for replacing that OR group because it's electronegative. Huge amount of stuff to worry about that later. But again, my R prime group is something carbon-based. It can be a benzene ring, it can be an alkyl chain, it can be an elephant, whatever you want, as long as it's got carbon in there. It can be an R group or an R prime group. So examples of esters, we will spend a huge amount of time on this. Aspirin involves an ester. There's the ester functional group, okay? And you've got to have that carbon there. If that carbon isn't there, it isn't an ester. Down here, you will make this stuff in the lab next term. It's the only organic reaction that you do that smells nice. All right, the rest of them smell like garbage. Isoamyl, this is not isoamyl acetate, is it? Yes, it is. This smells like bananas. So all of a sudden, the lab starts smelling like fruit. The ester here is embedded in this piece. We have the acyl group right there, and there's your carbon. That carbon on that second oxygen is what designates this as an ester, and not an anhydride, not a carboxylic acid, not an ether, anything like that. We will spend some time at the end of the second term trying to condense 3 chapters into what we call sort of applied chemistry. How do we use this stuff in the real world? And we'll talk about making polymers, polyesters, used in clothing a lot. These are used for plastic bottles, all sorts of different ideas. Again, you have to recognize the ester functional group. There's a carbon, there's your acyl group, there's your oxygen, there's your carbon. Now, my second quiz, which should be out there now, the second quiz will be due the week after, contains pictures like this, and your job is to pick out the functional group. Some of those homework problems, the same thing. And what we'll find very quickly is are we intimidated by this? Is this too much? Can we do this? And hopefully the answer is yes, we can. Amides. Amides are related to esters because you replace the O with an N. They're quite similar in terms of their chemistry, but amides tend to be much more stable. The reasons you worry about later. Amides are the building blocks of proteins. Anybody who's taken any biology would know that already. They have a very, very diverse type of chemistry. The stabilization is due to the delocalization, which we get into next, resonance possibilities in these systems. But again now, look at the possibilities here. When I had my oxygen here, I only had one R group. If I put a nitrogen there, because it's got more valence, I've got the possibility of adding more pieces. So I can start branching off. I can make more complex molecules by branching away from this nitrogen, and we'll make these things by coupling the N with the carbonyl, and this becomes very, very important in pharmacy, for example. So examples of this, some of which you might have heard of, glutathione, we already talked about the other day. This contains amides. These are peptides. A peptide is simply an amide in which you have a carbonyl next to an N. And I will point out, this is fairly dry stuff, but it's easy to get wrong. That's not a ketone. The N tells you it's not a ketone. That functional group is different. What functional group is this? Carboxylic acid. What about this over here? Carboxylic acid. Now, we haven't talked about this one yet. We will in a minute. But we're starting to get into some fairly dicey places where they do look alike. And it's very easy to get them wrong. The amide up here is simply the carbonyl with the N attached. That's the definition. And you'll see NN-dimethylformamide, or DMF as it's abbreviated, used as a solvent very soon. When we get into the chemistry, it's a very powerful, useful solvent to chemists. So amides, or amides if you're from different parts of the world, like we call them amides here, these are going to be very, very important to your future. And they're starting to look very much alike, so detail counts here. The last one we worry about, before we get back into some of the chemistry, are the amines. And amines are not amides and vice versa. It's very easy to trip up on this. So the amine is simply a nitrogen with 3 carbon groups attached, which are not carbonyls. The big difference there is there are no carbonyls directly on the N. If there were, it would be an amide, not an amine. Very easy one to miss this. Examples again, you can see this all over the place in pharmacy, medicine, material science, stuff like that. Very, very important, potent, functional group. We have morphine, which is related to things like heroin and codeine. We'll mention that in the near future. You can see here the nitrogen is sort of stuck in this cycle. That will mean something in a couple of weeks. And it doesn't have any carbonyls directly attached, so it can't be an amide. It has to be an amine. And now we can start to ask questions. I did this on Wednesday in recitation. I'll start doing it again on Monday. What do people think when they see something like that? Oh, crap. I mean, is that the case? They panic, or they worry, or they're intimidated by this stuff, or they start to think, wow, that's kind of cool. There's a lot going on there, and somehow I'm going to get my brain around this over the next 9 months. And at the end of the class, end of the 2 semesters, look at that thing and go, that's pretty straightforward, that, isn't it? That's the idea. So what we start doing is throwing these things at you now to get over that barrier, get over that intimidation barrier. So what functional group is this down here? Alcohol. What about this guy here? Alkene. What about this here? Carbon, oxygen, carbon. Ether. What about this one here? Alcohol. So again, we're starting to build complexity, starting out very simply, putting the pieces together, trying to get into next week, which is when the chemistry begins. We haven't done any chemical reactions yet. That starts on Monday. We are building the blocks or putting the building blocks together to do so. Aniline down here, very important in the dye industry, trying to make colorful things for dyeing clothes. It has the NH2 group attached and has the benzene ring attached. So this will be a complex molecule. You'll see a lot of this in the second semester. Guess what this smells like? Dead things, right? Some of these amines that have several functional groups smell awful. The other famous one is putrescine, because it smells putrid. These are decomposition products in biosynthesis as things tend to decompose, and it's a way of getting rid of nitrogen. So again, you can see the functional group. If I put this carbonyl on here, if I change this slightly, is that still an amine? What is it? It's an amide. So it's up to you to have a go at these things and practice them and be comfortable with them so we can actually use the language in conversation. Anybody? It's Friday, isn't it? It's a chance to catch up. So here's the deal. There's Taxol again. We started out by putting this up at the beginning of this section, and we said, look at that molecule. There's an awful lot going on there. After today, after we just finished that summarization of all of that stuff, you should be able to look at that molecule and give me every functional group in that system. Now, on my first exam, you know, I can tell you that on the first exam, there'll be something like this, a big, horrible molecule. Or, if you like this stuff, a big, beautiful, gorgeous, lovely-looking compound that you just want to know more about, because it's an anti-cancer compound and it's very important in medicine. What is this over here? Aromatic. Now, we did start off by saying, can you look at this thing and memorize it? No. Can you look at this thing and know something about its properties on the global sense? Probably not, because we haven't studied it yet. But even after 1 week of class, coming from freshman chemistry, you can look at that stuff and have some informed opinion about it. What is this functional group over here? Alcohol. What about this guy here? That's a ketone. That is a ketone. What about this down here? Carbon, oxygen, carbon. Ether. This one down here, we have a carbon, oxygen, carbonyl. What's that? That is an ester. Over here, what's that? That's an alcohol. What about this one right here? Amide. Amide. Now I can give you more problems if you want. I have a tutorial little video on the website right there you can look at to look at all these functional groups. It gives you another look at it. You can see it on your phone, your washing machine, whatever you use the internet on. Do it. Get it done, because it's now into the organic thing. We're done with the freshman stuff. We're now into the organic world. So we need to conclude this section by talking about pieces that you'll see a lot of, starting in about 3 weeks, maybe 4 weeks, that are not neutral, that are not stable, that are formed in chemical reactions. We know they are there. We can see them. We can measure them, and they are not quite the same as what we've seen, in the sense that carbon here all of a sudden seems to have 3 bonds, but it doesn't have a pi bond. This is quite different. So these will be called reactive intermediates when we get there, and we have to be concerned about the formal charges. So we could work this out if we wanted to. This one seems to have changed. We started maybe with, we started off quite early with CH4, but we've lost one of those bonds now. We have a 3-valent system. So look at that. How many electrons on that carbon in the middle? If it's become positive and it's lost a bond, what do you think happened to that bond? Did the electrons go away, or did the electrons get absorbed in? They went away, because you lose negative stuff, you become positive. So how many electrons do you think are around that central carbon? Keep going. It's got 3 bonds with 2 electrons each. Hey, there we go. Right? That's a 6-electron system. Right? That's my little thing to show an electron, E with a minus charge. 6 electrons. These are called carbocations. These things you will like a lot, or not. They do form, and we have to worry again. How do you calculate this if you're not quite sure? It's group 4, take away 3 bonds, no spare electrons, that's +1. Use the formula for formal charge, you get that answer. So then you'll have to worry about what else is here. How many hydrogens on that carbon if it's got 3 bonds? None. None. The 4th valence is the positive charge. That's a bit different. You've seen positive things before, like hydronium ion, but this is the opposite now. This is where the central atom has lost a pair of electrons to become something reactive. If you look at the middle here, that again is called a carbocation. That thing will need electrons. Its whole purpose is to become stable by picking up some electrons from someplace else, which will define its chemistry in the near future. But again, it's, in this case, 3-valent. We haven't drawn the hydrogen. There is a hydrogen here as well. And the positive charge is telling you that that carbon lost a pair of its electrons. It wants them back. That will be the motivation for its chemistry. Head towards the end. We'll define these things later with terms like tertiary, secondary, primary, but that's a long way away. You've got to worry about what else is here. How many hydrogens are left on there? 2. I've only got one bond to carbon, I've got a valence now, which is a positive charge, and I've got two hydrogens. Now, some of the questions out there on the homework are trying to probe if you understand these things. What do you think the hybridization pattern is right there? If it's got three single bonds, what does that match? sp2, yes it does, sp2. They're all sp2 hybrid carbons. What shape is sp2? Trigonal planar, flat. These things will be flat. That's a month away. That's the same idea. The rules that we learn now are going to start to be put into practice. Second semester is all about this. Second semester is all about making carbon negative, because then we can use it as what's called a nucleophile. We can use it to knit together with other pieces and make carbon chains and make bigger molecules. Very, very powerful stuff. But this now is a little bit different. In this case, it's lost a bond to something, but instead of losing the electrons, it absorbed the electrons. It picked the electrons up. So now it's become something called a carbanion, a negatively charged carbon. And this thing will not be very stable, and it will be very powerful in terms of its base properties and its nucleophilic properties. But again, we at this point need to worry about its hybridization and its shape and its valence. How many electrons are around that central carbon? 8. Where do they come from? 3 single bonds, that's 6, plus the lone pair. This is carbon with a lone pair. A little bit different. So with that in mind, think about its hybridization. It has 4 valences that all look like maybe ammonia, or it looks like nitrogen with 3 bonds and a lone pair. What shape are we talking about? What hybridization are we talking about when you have 4 valences, one of which happens to be a lone pair? sp3. sp3, and what shape is sp3 typically? Tetrahedral. You might argue it's a little bit twisted or a little bit away from tetrahedral, but it's roughly tetrahedral. My point is, you already know this stuff. You can project forward if you understand it and you've studied it, and you're confident with it. Fair enough? Those are the two types, or the major types of carbon species you will see over the 2 semesters. You'll also see radicals in the near future, but they're not charged. And these will be called intermediates because they don't last very long. So the last thing to do before we get into one of the absolutely fundamental important ideas of delocalization, which is key for understanding what's to come, is to worry about lone pairs. And to me, lone pairs are very important because that's where most of the chemistry happens. When we worry about a mechanism and how things happen, typically it's the lone pair somewhere getting involved. Something positive goes to attach to a lone pair, all of a sudden we get some chemistry. So this chart, or this table, it's not that busy, it's not that bad, and I want to try and relate some of this stuff to things you already know. I think that's the easiest thing to do here. What is the simplest species you know, oxygen with a negative charge, from your previous lives in chemistry? Hydroxide, okay? So again, keep it simple. I was taught to do this, and I think it works, even at 30 years on. Hydroxide, OH minus. That minus means it has an extra lone pair compared to water. It absorbed a pair of electrons. So hydroxide will exemplify the more complex organic molecules. This doesn't look anything like hydroxide, but it reacts an awful lot. If you put your hand into a bottle of hydroxide dissolved up in water, what happens to your hand? It hurts. If you dissolve this stuff up in a solvent and you put your hand into it, it hurts for exactly the same reason. It's a reactive species. And it has the same number of lone pairs. So if you can remember hydroxide, it has 3 lone pairs because it needs to have 8 electrons. It's only got 1 bond, so the other electron pairs must be lone pairs. If you understand hydroxide, you can extrapolate to the organic world. Each of these species above, which have organic pieces attached, the business part of the molecule where all the chemistry happens is still the negative oxygen, just like it is for hydroxide. So extrapolate. Here, 3 lone pairs. Why 3 and why not 4? 4 would break the octet rule. The universe would explode. That wouldn't be good, right? So 3 lone pairs, it's already got 1 bond. That's 2 electrons. 3 more gives you 8. 3 pairs gives you 8. Simple enough. Keep it simple. What is the simplest non-organic molecule that you've dealt with before in which a central oxygen bonds to 2 other things? Water, right? H2O. Go and do this. H-O-H. How many lone pairs on the central oxygen? 2. Now we know that from the octet rule. That exemplifies an awful lot of organic chemistry in the near future. If you look at the species above, this does not look like water, but it does a lot of the same chemistry. It has a lot of the same properties. It's very polar, dissolves up polar material. Look at that. All I've done is swapped out a hydrogen from water for this carbon piece here, and the oxygen has the same pattern. It has 2 lone pairs. Not 3, not 1, it has 2 lone pairs. Down at the bottom, second semester, carbonyls. Even though it's changed its hybridization, the oxygen has 2 bonds, one of which is sigma, one of which is pi to its adjacent carbon, but that's only 4 electrons. To have 8, it needs those 2 lone pairs. And if you look at those hybridization patterns, that should make sense, and where they came from should make sense for those pictures. So that's what you remember. Remember water? A divalent neutral oxygen will always have two lone pairs, just like water do. Keep that with you. How about the opposite example? What's the simplest positive species you know of oxygen with three things attached? Hydronium, right? H3O plus. So let's keep this simple. We don't need to make it any more complicated. Let's keep it simple. The middle oxygen has a charge, a positive charge, because it shared electrons with something else, and it has one lone pair to make 8, right? To make 8 electrons. That's all it is. So if you remember this hydronium ion from the past, you know a lot about the species above. You can see here the alcohol, the protonated alcohol, looks a lot like hydronium. If that was an H, it would be hydronium. Bring it with you. Down here, protonated ether looks nothing like H3O+, but it does. And this pattern recognition now is the key to doing well, getting away from the simple stuff from the freshman level and getting into the more complicated ideas. Because you'll see these things as reactive species in chemical reactions, and if you understand them, it's not that difficult. Down here again, protonate that carbonyl, take up one of its lone pairs, make it 3-valent, it must have a positive charge, just like H3O+. So keep an eye on that, keep this with you, and use it as we start to go further. Everybody okay? Michaela, you all right? Anybody at the back? Is anybody at the back? Delano, you all right? Good man. Okay. The opposite can be said when you think of, I'm sorry, go back a second. You've got to worry about carbon with a negative charge, we call that a carbanion. You've got to worry about oxygen with a negative charge, these are very important species, and you've got to worry about nitrogen. Okay? Nitrogen we save for the end of the second semester, it's a ways away. But we do collect it here now so that we can see where these groups come from, and it's the same idea. So I'll start in the middle, because you're not so familiar with nitrogen as you are with oxygen. What is the simplest nitrogen-based molecule you know of that has 3 single bonds? NH3, ammonia. Okay, I'm going to say NH3. So I've got my central nitrogen, I've got 3 hydrogens attached, and I've got 1 lone pair to make up 8 electrons. You know about this molecule already. You know something about its structure, and you know something about its chemistry. You've used this stuff in the past. Well, the molecules above it, the organic pieces, look an awful lot like that ammonia. In this sense, you can see now, all I've done is taken off 1 hydrogen and replaced it with a carbon. And I'll tell you now, those carbons don't do anything. Those carbons are just there for structure. They don't do any chemistry. So I can see here, 3-valent nitrogen, neutral, 1 lone pair. Now, go to the left. You don't know too much about this stuff yet, but if you take off one of those protons and you make NH2 negative, we do use this molecule, and it's a simple one to pick up. This is negative because it absorbed electrons. And this will make sense because nitrogen's electronegative, it wants electrons. So making that negative is not such a big deal. Well, the molecules above it don't look like NH2 minus, but they are very similar. At the top, 2 valences, 2 lone pairs, nitrogen must be negative. Down here, same. Down here, same. They all look like very different species, but what we're trying to get across here is that you can learn this stuff quite systematically, and it's not that difficult because they're all the same type of thing. On the right-hand side, if you have 4 bonds, you probably have seen this before, ammonium. If you put 4 bonds on the N, you have to use that lone pair to form one of those bonds, and so you lose the lone pair. There's no lone pair right here, and you put the positive charge there to make it make sense. Species above, we'll deal with ammonium salts second semester. We'll deal with these guys a lot next term. We'll deal with this next term. If it has 4 bonds, you've used the lone pair. It can't have an extra lone pair because then that would break the octet rule. No good. Fair enough. Nothing tricky there. Okay. So I'm going to finish this, and I'm going to get myself 10, 15 minutes dealing with this topic. And you're going to spend the weekend thinking about it, and then we're going to deal with it again on Monday. I think it's fair to say we're not in the freshman stuff anymore. We're starting to get quite complex. There are lots of ideas that we're laying out as basic terms and basic concepts to be able to play this game. On Monday, we start chemical reactions. They happen to be acid-base reactions, some of which you've seen before, but we'll teach it in a way that you've never probably learned it before so that you can use this in a proactive sense to solve problems and to maybe do new chemistry. But we still need to finish off this idea of language, this idea of this is what you will see. These are the terms you will see. These are the concepts and the sort of framework that you will see. We have mentioned this in the past. I've mentioned it in recitation. I did it in lecture a little bit. We have to worry about some of these 3-dimensional ideas. What is the suggestion there with that wedge? What is it trying to show? It's coming out towards you. Chapter 5, I believe it is, when we get into this whole idea of molecules related as mirror images, like your hands, and they have different properties based on that. You can see here now that this is important. Molecules are not flat for the most part. And we've developed these little devices to be able to show that, to show the chlorine coming out, because it's not going in. It's pointing in the opposite direction to the other chlorine. We have to show that. So this one is coming out, and that dashed light there makes sense. It's going away from you. It's starting to fade out as it goes away. And that then is the opposite. That then is going into the plane of the board, of the paper, whatever. It's behind the molecule. So we need to be careful there. We can use these on cycles. This is suggesting that this is pointing in the opposite direction in space to that. Huge amount of stuff to come soon about that idea. And again, trying to show relative sort of disposition around the molecule. This is going down, this is coming out, this is coming out. Very straightforward so far. In the 2 weeks, once I get to that chapter, maybe 3 weeks after the first exam, not straightforward at all. You have to start thinking in 3D with a flat piece of paper in front of you. It's tricky. It's kind of fun, but it's tricky. At the bottom, again, we use different depiction. This is called a Fischer depiction. This will be very important next term when we start talking about carbohydrates and amino acids. A very quick way of representing lots of information in the structure. So don't worry about that too much just yet. You've seen it. You know what it looks like. A Howard projection, second term. We'll see a bit of that this semester maybe. And then what we call bicyclics. That slide is important for the future. Know what those things look like so you can recognize them, but you don't know how to interpret them too well just yet. You don't know about cis and trans and isomerism and all that stuff. That will come soon. But just recognize if you see this type of picture, that's a Fischer depiction, which is used for a certain type of analysis in chemistry. Ashley, you all right? Anybody at the back? Johnny, you all right? Good man. Now, we've seen this stuff. We have built quite quickly now a terminology. We've built a collection of ideas that we can use to discuss chemistry. Then we can move into chapter 3 and do chemical reactions. But the very last topic at the end of this chapter is this. And this confuses everybody at the beginning. This is not a simple thing to get your head around. You must get your head around this because it's going to underpin a huge amount of ideas throughout the 2 terms and biochemistry. If you've taken physics, you know a bit about resonance, but this is a totally different resonance. This is not the physics resonance. This is not pipes and noises. This is quite different. We'll find out that over the years, chemists have developed different ways of drawing these molecules to convey information so that somebody reading this knows something about these molecules. This is acetate. It's a very simple system. It's formed by taking a hydrogen off a carboxylic acid. It's a negative species. We'll call it the conjugate base next week. And the way this is drawn as a Lewis type structure to try and show all of the bonds and atoms where they are, the connectivity between them and the electrons around those atoms is quite limited. It is quite limited because what is suggested here is that this is a double bond and that this is a single bond. So this would be sigma plus pi. We can build that up from last week, hybridization patterns, and this one would be sigma. Now, what, does anybody know? Which is longer, a single bond or a double bond? A single bond, okay? A single bond is longer. So this picture, as it's drawn in its limited way on a piece of paper, is suggesting to you that that bond at the bottom is longer than the bond at the top. If you take this stuff, the crystals from the bench, and you go over to Ward Beecher and you talk to Dr. Zeller, the crystallographer, and you put this stuff into his crystallography machine, and you get back the picture, those bonds are exactly the same length. What? Right? In reality, those bonds are exactly the same length. So this is where bonding started to change in terms of the ideas, in terms of the complexity and subtlety. This molecule does not look like that, but that's the best we've got in terms of writing it down as a simple Lewis dot structure. Somehow we have to correlate the two, we have to make the two sort of match. Well, what's going on here is something called electron delocalization, resonance. The actual structure is more like this. I'm starting now to use a little bit of a different thing, a dashed line. A dashed line suggests partial bond. If you think about what bonds are, on your experience so far, it's a pair of electrons either sat on an atom or it's a pair of electrons shared between atoms, and those constitute bonds. Now we're suggesting that bonds aren't necessarily sat on one atom. They aren't necessarily sat exactly between two atoms. They are spread out. So this is a limited picture, but that on the right is a more useful picture, a more correct picture. So what's going on here is spreading out of electrons. And I'll go back a second and put my lone pairs in. We are suggesting that 3 lone pairs are sat here and 2 lone pairs are sat there. The negative charge is a lone pair. The species on the right, or the picture on the right, is suggesting that that extra lone pair is not sat on that oxygen. It is actually spread out amongst the 2 of them. And if you think about the electronegativity of oxygen, what is it? 3.5. It likes electrons. So there's something going on here that allows that lone pair to be spread around the 2, because they both have, they both have attraction for those electrons. So what we're going to see as we draw pictures here is that we can push those electrons around. We start to use arrows to be able to delocalize things, to be able to show things. I've got to be very careful here. You've got to be very careful here. This is not equilibrium. We are not going backwards and forwards. The electrons are not bouncing over here and bouncing back and bouncing over there. That's not what's happening. They are spread out. The best I can do for this is a piece of toast. Okay? You take the piece of toast, you take some jam or some butter, and you spread it across. The butter is delocalized. I don't know if that works. It works for me. I like toast. You spread the butter out, it is delocalized, right? It's spread across the whole system. It's not jumping backwards and forwards, because that would be weird. It is spread out. That's what's happening here. So we have to bring in a slightly new device to be able to describe this. And this is the first introduction to the resonance arrow. You will see probably 5 different types of arrows in the class. You've already seen equilibrium arrows in the past, you've seen reaction arrows in the past, you'll see a whole bunch of different types of arrows that are used to describe different ideas. Now, what I need to point out here is that this now is new. This is a resonance arrow suggesting that this is a delocalized system. This is not, we've got to be very careful here, this is not this. It is absolutely not that. So let's take our time with this. I've got 10 minutes. I can show you some pictures. I can come back on Monday and we can look at it again after you've had a chance to digest. The system here is not jumping between 2 pictures. These 2 Lewis structures, the first one is the same as the one above on the left, suggesting that 3 lone pairs live on one oxygen and 2 lone pairs live on the other. The other Lewis structure is suggesting that now we have 3 lone pairs up there and 2 lone pairs down there. Not what's happening at all. This is the best we can do on a piece of paper. This is to show where the electrons can be. So we have to worry now about the physical, what's going on. If it's not equilibrium, it's got to be something different. It's spreading out. We're not jumping between the 2 pictures. We're spread out. So what I'm going to say is that these 2 pictures are not different molecules. They are not different structures. They are a representation of where the electrons are in the one molecule. So that setup right there, that whole idea now, that is one molecule. I will learn to write on this thing eventually. That's one molecule, not 2. This will be very confusing. So be careful. Different type of arrow. We don't have the equilibrium, we have the resonance arrow. And again, why do we do this? It's a limitation. We don't really have anything better we can do for this. It's a way of writing down Lewis dot structures, but representing delocalization. Think about questions over the weekend, because this will be confusing. So let's take this a step further. Let's look at some systems in which this happens, and let's worry about how to draw these pictures. Where do they come from? On the left at the top, all I've done here is extrapolated this to a bit more complicated system in which I have a benzene ring right there, and that isn't going to do anything. The delocalization is here between those 3 atoms, and that's a bit of a clue. For a delocalized system, you need 3 atoms. Typically, you're looking at some charge next to a pi bond, or some lone pair next to a pi bond. That pi bond must be there for this to happen. So we're going to see a generic sort of system. We could argue this is a double bond with X at the top, Y in the middle, and then Z or Z down there. And we've got to have something like this for delocalization to happen. If you just have single bonds in your system, no delocalization. If you have a pi bond and something next door to it has extra electrons or not enough electrons, you'll get delocalization. That's what you're looking for key here. So I got these 3 atoms in which I've got charge, and I can spread it around. So where did this come from? My other picture. You can get these pictures and you can build them yourselves. All I need to do is push a lone pair up onto that oxygen. I'm using a curved arrow, a curly arrow, to do this, to show how this is happening. Be careful though, this is not dynamic. The electrons are not moving around, they are spread out. That then gives me a second structure in which my pi bond now seems to be here and my lone pair seems to be there. That's all I can do, really. Those are the important resonance structures for that system, and that now gives me an idea that this molecule is spread out. The charge is spread out. So if I wanted to draw a resonance hybrid, let's call it a hybrid, bring those two pictures together and draw the dashed lines. What would it look like? Well, when you start worrying about resonance structures, you must first of all remember the connectivity never changes. Where the atoms are related to each other does not change. So carbon is still bonded to two oxygens. It's the electrons here. So I'm going to draw my connectivity out like so. I'm going to draw my dashed lines. I'm suggesting now that this is a partial bond and this is a partial bond. That's a better picture, but I need to finish this off by putting my charge in some place. I could write this. Watch this. Do I have a device so far that allows me to show a little bit of charge? Delta. In this case, delta negative. So I'm going to write this, delta negative. That one is delta negative, and that one is delta negative. They both share that extra lone pair. They both have a little bit of extra electron density, and therefore delta negative. That's a reasonable picture. And we'll call this a hybrid. I'm going to hammer this in recitation. Tyler's going to hammer it in SI. It needs to be understood now, so we can use it in chapter 3. Well, at the bottom, or in the middle, I should say, I have a slightly different picture. But it isn't different. I have a lone pair next to a pi bond, just like I did above. And I can push one of those lone pairs, doesn't matter which one it is because they're both the same. I can do that. I can spread that charge or that lone pair out into the carbonyl. And that will give me a picture over here. Why is that now positive? Why does it have to be positive? How many bonds does it have? How many bonds does the oxygen have? 3, right? So H3O plus must be positive. It's the same idea. What does this remind you of? Why is this negative? 1 bond to oxygen. Why is it negative? It's like hydroxide. It's negatively charged. So that is a resonance structure for this. And the actual overall molecule will have some structure like this, where it's spread out. And this will be delta negative, and this will be delta positive later on. That will explain a lot of its chemistry, based on delocalization. Go ahead. Haley? Taylor, that's the one. Toast. Spreading out. We're not moving. Dynamic. Toast. Just think toast. You'll be all right. Yeah? I get toast on my exams. People will write things about toast on my exams. And Harry Potter and stuff like that, but, you know. That's usually an indication they're not doing very well. Spreading out here. We are spreading out electron density. We'll do it for positive pieces. We'll do it for negative pieces. Now look down here. I've got a system, very important in the second term, in which if I drew the actual molecule out, I think most people would draw this picture. They would draw that because everything has 8 electrons, it obeys the octet rule, and it's a stable, sensible molecule. But a lot of the chemistry in the second term comes about because this pi bond is polarized towards the N. Now, why is that logical? Why should electrons go towards N and not towards C? More electronegative. Absolutely, it's more electronegative. Jordan, go ahead. Electron what? Diffusion. Diffusion, I'm not too sure we should use the word diffusion because that's a dynamic process, isn't it? Diffusion means moving. It's spreading out. It's toast. You've made toast in your life. You take some butter and you go like that and your butter is delocalized. It's not moving. So I've got on the left a picture which now will describe a lot of the chemistry of this molecule. We'll see next term, I write delta negative on the N and I write delta positive on the C next to it because of the electronegativity difference. And that can be represented by this resonance structure. Not an easy thing to get your head around at all, but we must by Monday. Ashley. So in this example down here, if I concentrate on the really important part of the molecule, which is here, and don't worry about the 2 radicals attached, I would draw that, right? Where the suggestion is that the pair of electrons from the pi bond are closer to N than they are to C. Mr. Metz. Now I'm going to hold off on that question until Monday. I'm going to answer that on Monday. I don't like curved arrows and resonance structures myself, and you'll see why on Monday. I'm not done yet. That's not a suggestion we're going anywhere yet. You have 2 minutes. You're paid for 2 minutes. You ought to get those 2 minutes. We are going to look at different types of structure. We're going to look at negative charges and positive charges, and then later on something called a radical, which is halfway between. So what I need you to do between now and Monday is get happy with this 3-atom system. When we move into allylic chemistry later on, this is a positive charge now. What do you think a positive charge needs? It's lost a pair of electrons, it needs some electrons. Well, look at this next door. We've got some electrons to help out. We could draw a second resonance structure in which that pair of electrons is spread across that system. It's not dynamic, it's toast. And I can draw a resonance hybrid in which those electrons are spread out. So I might have delta plus on this end and delta plus on this end. And it helps out because it helps stabilize the molecule. And a general idea over the weekend and in the future, if you can spread charge out, it helps stabilize the system. That's what you're after here. This is a good thing. It will help stabilize things. And next week when we start chapter 3 on Monday, it will help explain reactivity and stability, which is where we are going on Monday. So today was the end of the sort of introductory stuff. We're done with that. Monday, wow. Be ready.